actually is. Okay, so this is how you set it up. I'm just jumping down to this part. 98 times 12. That's the time sign. That's the speed. Okay, so 98 times 12, square root of that. Wow. 34 meters per second. So like 70 miles per hour. So that's, I'm guessing that's about 12 meters. You're going around that circle at 70 miles per hour. I don't think I'd make it around more than a couple of times probably. Okay, good. So that's why we're even talking about this human centrifuge. It's not an amusement park, right? It's for other purposes. Any questions on that one? Okay. Let's look at this one. Yep. Thank you. So the first three from homework 7 are from chapter 3, actually. In this one, a roundabout or a traffic circle, cars go around a 23-meter diameter circle, so be careful, that's diameter. If the car's tires will skid, if we have an acceleration greater than 0.6 g's, what's the maximum speed? So really, this is the same as the centrifuge problem. The acceleration is 0.6 g, so you'll have to figure that out. You might have a different number than I do. And another difference is they give us the diameter of the circle. We need the radius. So just divide that by 2 to get the radius. This is the acceleration, 0.6 times 9.8. And then do the same thing, solve for v. Okay? So we've done some similar ones to this one. Let's see what this third one is. Okay, so in this problem, a particle rotates in a circle, centripetal acceleration of 9.2. What is the acceleration if the radius is doubled without changing the speed? And the other part, what is the acceleration if the speed is doubled without changing the radius? All right, so let's actually put this one together. I mean, we can try to guess what would happen, but that's not the best way to do it. Let's look at the actual formula and figure out what will happen. Kind of like the one you voted on, actually. Okay, good. So you know that this is how these things are related to each other. So the acceleration is this. And you might have a different number than I have. This is, the one that's towards the center, because you're going in a circle. What is the acceleration if the radius is doubled without changing the speed? So what if you suddenly made the radius twice as big, but you didn't change the speed? So if you made the radius twice as big, you'd have to cut this in half, right? So double the radius means that this is half as much. Okay? Without changing anything else. So half of 9.2, or whatever your number would be. So again, you can't just guess. You might think double the radius, that means you double the radial acceleration, but you don't, because it's related to 1 over r. Another way of thinking about it is, well, if you made the radius twice as big, then that would be an easier turn, right? Than you're trying to go through a tight turn. Okay, good, so half as much. What if you double the speed for the second part? That's kind of like the one you voted on, actually. Now, if you doubled the speed here, if you made this twice as big, you've got to square that 2, so it would be 4 times as big. So part B it's 4 times as big as this, just like the one that we voted on earlier, right? You have a new speed. Let me write it like this. The new speed, that's what the prime means, is twice the old speed. Okay, so if I want, I can plug that in here. So this would be, v prime squared over r. But v prime is 2v. So this turns out to be 4v squared over r. That's more maybe of a mathematically rigorous way of looking at it. Let me just go back over that. So the new speed, the primed speed, is twice the old speed. So I could put that in the formula. It's just v squared over r. This is what the v is. But I also know I've doubled it, so I could put this back here and square it. So then I've got 4v squared over r. So 4 times that. 36.8 or something like that. Okay, good. So that little bit of chapter 3 just introduces this idea of acceleration towards the center. The other thing I would say about that is we'll see something like this. We can get the speed this way. If you go around a circle one time, you go around the circumference of a circle, which is 2 pi times r. Right, that's the distance around a circle. And then we'll have a specific amount of time called the period. He tells me the lights are going to go on. Yep. So the period is the time to go around just one time. So it's not tension, it's t. We used t for tension before, but this is the period. The amount of time to go around once. So we could use that with some of these circular motion problems. We could also write this in terms of something called the frequency. So the frequency is 1 over the period. So this is, the units are 1 over seconds, which is a hertz. It's the amount of revolutions per second. Cycles per second, whatever, oscillations per second. So however many things per second, that is the frequency. And it's the inverse of the period. Okay, so here's what we've had so far today from this chapter. Acceleration towards the center, and then sometimes we can solve for the speed this way, or in terms of the frequency that way. Okay? So, keep that in mind. Oh, it's already on. Nope. There we go. Okay, so this is what we've seen so far. Again, v squared over r towards the center. That's the magnitude of the acceleration. There always has to be some kind of force towards the center. So here a car is turning a tight corner at a constant speed, and you got the overhead view of this. The direction of the acceleration in this picture is south. It's got to always be towards the center. And the magnitude, again, was v squared over r. If you make r smaller, keeping v the same, the acceleration has to be bigger, that sort of thing. Okay, good. So that's kind of a synopsis of what I've just said here. So, south. So a ball at the end of a string is swung in a horizontal circle. What is the direction of the acceleration? So that's this situation. I'm going around in a circle. The ball is at the end of a string. Which way is the acceleration? So tangent to the circle, that would be in the same direction as the speed, or towards the center. Okay, so a good voting one. Excellent. Nice, thank you. Good, okay, good. Nice, nice. Huh, so kind of a mixed bag here. It's towards the center. Remember, the acceleration is always towards the center. So even though the speed is tangent to the circle, the acceleration is always going to be towards the center. If you cut the string, the ball would just go off in the same, tangential direction. Okay, good. So this is another way of looking at this. We talked about the period, which is the time to go around once. The frequency is just 1 over the period. So 1 over seconds or hertz. The amount of times you go around per second. Could be less than 1, could be 1, could be more than 1. So if you want, you can take this equation for the speed that you see here, and then, or this one that you see for the speed, and plug it into the radial acceleration formula that we had before, this one. So a couple of different ways of writing this. So take this is where we started with, v squared over r. Plug in this formula for v, so 2 pi f times r. You can plug that in for v, that's what's being done here, and square it, and you get this relationship. Or you can take this one for v and plug it in and get this relationship. I guess what I usually do is just think of the acceleration's v squared over r, and then I remember that I also have these other ways of looking at it. Okay, so keep that in mind. Let's take a look at 6.1. So we have a 5 meter merry-go-round that's turning at 4.4 seconds. That's the period. That's the time to go around once. What is the speed of a child on the rim? Okay, let me just draw this out and say a few things about it. Okay, so if you're going around in a circle, this is the overhead view. Going around a circle, the speed, 2 pi r divided by the period. So as you go around in a circle, we'll just say we're going this way. When you're out here, going around the circle, so if it's a merry-go-round, if you're at the edge, you have a greater speed than you do if somebody is closer, right? If this goes around once, this position would go around once. So you're going around once, so you have the same period, but if the radius is bigger, your speed is bigger. So if you're riding a merry-go-round and you want to maximize the amount of fun you have, if you like going fast anyway, go out to the edge. And that's where you actually go faster. So picture yourself doing that. If you're at the edge, you go faster. You go towards the center, you're not going as fast. Okay? I don't think they make merry-go-rounds like they used to, do they? There's like just a few around anymore. I think the ones that you can find have like some kind of governor built into it too, so you can't go too fast. When I was a kid, like they had super ball bearings in it and you can just start flying around, but they've decommissioned a lot of those. Anyway, for this one we have everything that we need to solve this. So 2 pi 5 meters and then divided by 4.4 seconds. And that'll give us the speed. For fun, let's just see what this is. 2 times pi divided by 4.4. So 1.4. Is that right? Oh, I forgot the 5, didn't I? Times 5. 7.2. Okay, so about 15 miles per hour. That's not too bad because it's a relatively small radius, right? Ah, what did I do wrong in this problem? Good, yeah, they actually give us the diameter. We just need the radius. Okay, so this is not right because this should be 2.5. Okay, and then this is half as much, 3.6 instead. Okay, thank you. Yeah, be careful, diameter and radius. All right, any questions on that one? Okay, good, so I will, the homework 6 has been extended till Sunday. Any questions, let me know. We can set up a Zoom meeting. I had a few of those earlier in the semester, but they've kind of tailed off, so don't hesitate to do that. In this kind of new COVID semester, don't hesitate to contact me on the weekends. It's like every day is some kind of a little bit of work, so do that. Take advantage of it. And I'll let you know from homework 7 which problems I think you should look at. We've done a few of them today, Probably maybe just a couple more from homework 7. Not due till after the test, but I think it would be good to look at them for the test. And then the lab tomorrow is online. I'll let you know when that's up, and that sort of thing. Any questions on anything? Wow, so almost a 2/3 mark right after next week anyway. Excellent. All right, well, if there's no questions, that's all for today. And then I will see you next Wednesday, I guess. Unless we do a Zoom meeting, then I'll see you then. Okay.